There's a lot of brave speakers at this conference who are willing to try their hand at live technology. I appreciate the efforts. This is the way the future is going. The models are going to be online. The design team are going to be talking to contractors on iPads. And for Obayashi to invest in 4,000 iPads, not only the people in Apple are very happy, but I'm sure the staff are very happy that they all get a free iPad. So it's definitely the way it's going. Our next speaker is all the way from Australia. I met him on Monday evening for the first time. Brett is come today to speak to us about infrastructure. He's here from Autodesk, and I think he's going to show us a bit about InfraWorks. And Brett, you've got 6 minutes.
Well, I'm not so brave, so I'm not going live.
Don't forget you are on YouTube.
Hi, Mum. Go over that, please. Yep. Great. Okay, thanks again, Rowan, for the introduction. We've seen a lot today about the vertical building space, and the vertical building space has been mature, I think, in a BIM technology sense for a very, very long time. But the next frontier is the horizontal or the linear building space, or what we call, or what we term BIM for infrastructure. And what I'd like to show today are some of the solutions that we've come up with for the BIM for infrastructure technology from Autodesk. So first of all, I'm not going to show you the BIM wheel, because I think everyone's seen the BIM wheel to death. But what I wanted to highlight was some of the challenges that we have in an infrastructure space. And when we talk about BIM in an infrastructure sense, one of the things that we look at is efficiency, agility, so the ability to have the model dynamic, but most of all, BIM for infrastructure reduces risk. Forget about everything else, it reduces risk to the project. Because when the excavator and the workmen turn up on site, that BIM philosophy and the BIM technology gets very real. We start digging dirt. That's when it becomes applied technology. At Autodesk, we look at different technologies, and we look at different types of technologies and emerging technologies. And what you're seeing on the screen are some of those emerging technologies. And we build technologies around these emerging technologies. And some of the things that you're going to see today are BIM digital cities, BIM in the field, reality capture, which we've already seen a lot today. We're going to talk about that in a moment. Maybe some simulation. What we're also going to show is what we term transformative technology. And we're going to show some examples of the transformation in technology. So the first example that we want to talk about is what yesterday's world looks like. Now, this isn't today's world, this is yesterday's world. And it's a world where we deal in megabytes. I don't think I've sent a megabyte file in 5 years on email. So internet file sharing, you've seen a lot of talk about cloud. My opinion of cloud, and some of the opinions at Autodesk, is that the cloud not only is a very useful tool for storage and collaboration, but the cloud is going to enable us to solve engineering problems that we've never been able to solve before. So that's our philosophy around cloud. And then here's today's world, or the world that we'd like to live in today. Dealing with terabytes, procedural design, rules-driven design. And these are the technologies that we look at, and we implement them in our software and our technology. So the first thing that we want to look at is how we've transformed the landscape with data. The whole philosophy around Autodesk building this tool is that not everyone is a GIS expert. Not everyone understands geographic systems and GIS and shapefiles and all of that technology. All the users want to know is, I need to do something in this space and I want you to build it for me. And that's what we've done. So using these tools, we can zoom to anywhere in the world. We can select an area anywhere in the world, and using the cloud technology, the Autodesk solution will go away and build that. So what you're looking at is an area here in New South Wales in Australia, and what I'm doing is just selecting a specific area where I need to do some design. And the software will go away and it will understand that area, and it will start aggregating some of the data sources, some open source data. And what it will effectively do is go away and build that for me in 3D. It takes around 10 to 15 minutes, And in that time, you receive an email and it says, yes, we're done. We've done it. On the dashboard inside the software, you refresh the dashboard and the model appears. And it's not a very big model. I don't know whether you can see, but that's about 200 kilobytes. Ignore that comment about megabytes before. So very small model. But what it's done is it's gone and built that in 3D. And I haven't done anything. I don't know about projection systems or coordinates or transformations or anything like that. I just know I need to do something there. So that's transforming data. That's big data. The next technology we need to look at is a technology around road design. And for a very long time, we've had a road design solution. But all of the road design and civil design solutions aren't really that dynamic, and they take a long time to change, and they're not very adaptive to change. And when you're doing a proposal for a road, a bridge, and a rail line, you need to be dynamic. You need these models to be able to change. And in an architectural sense, you're able to do that quite easily using the current technologies. So what we've done is that we've built the technology that enables us to do this. So what you're looking at is a real engineered road in context, in canvas. So what I'm doing here is starting the road design process. It's giving me immediate feedback on the design rules. So where we're seeing the colorization of those curves, that's saying that I comply with a design standard. And then I can start making changes to that road. And I'm doing all this in canvas. I can move the road. I can change the vertical profile of the road. It doesn't have to be a road, it could be a rail line. I can start then making immediate changes to the vertical profile of the road. So this is transforming road design. All in canvas, all in 3D, rapid road design. You can see as well, we can start changing the way the road looks and the way the road performs. And what I'm doing here is I'm adding a passing lane to that road. I haven't changed any components. It hasn't taken me a day. It's taken me 1 minute to do. And the next thing I need to do is I'm going to change the way that the road interfaces with the existing surface. So I'm changing what we call the cut and fill batters. Again, it's not hard. It hasn't taken me a day. I haven't had to go and find more information. I'm doing this dynamically in canvas. And so in a very short period of time, you've built up your road design. That's a real engineered road. The next technology that we're spending a lot of effort on are bridges. And bridges, historically, and I'm sure we've got some bridge designers in the room, they're the Stephen Hawkings of our engineering world. They are very, very smart people. And bridge design is a very, very difficult science. But what we've decided to do is make it easy. So here we have a road that crosses a water body. And what we're going to do is we're going to select the road, and in 2 clicks, we're going to have a bridge. So start chainage, end chainage, bridge. And that is quite simply almost an engineered bridge. There's other things that we need to do to the bridge. We need to do code checking and grillage and that sort of analysis, and we're going to do that. But now what we're doing is going to make the bridge look like a bridge. It's adopted the road style. Now, if I was to do this in the traditional civil design packages, this might take me, I would suggest, a day. And I've simply clicked 2 positions and it's put in the barriers and the concrete and the Jersey barriers and those sorts of things. Now what I'm doing is there's something in the way, so I need to move the pier. Well, that's fine. Let's move the pier. The other thing that we need to do with bridges is we need to adopt what we call localization. Bridges need to adapt to very local specific rules. And what we've got here is we're going to change what we call the girders to a localised girder set. And in this case, we've got all the British girders, AASHTO girders, but because I'm in Australia, it's an Australian girder. And why do we need to do this with the girders? Well, what we're actually going to do is we're going to simply click the bridge and it's going to tell us how much concrete and steel goes into that bridge in 1 click. So there's our new girders. We've got exterior and interior girders. And what we're going to do now is we're going to simply change some of the components of that bridge, some of the dimensions of that bridge. So we can do that as well. Nothing hard. It hasn't taken me hours. We're just changing the components. And now what are the quantities? In one click. Now, if you have a road project that has 20 bridges, that's powerful, that's transformative. In the infrastructure space, we haven't quite moved to model as a deliverable. And that, I think, is probably some way off, in particular in Australia. So what we need to do is documentation. Now, documentation can take a long time to do, and it's a very arduous task, and even just setting up the sheets relative to the new road or bridge can take sometimes weeks. And I've worked on projects where it has taken weeks just to set those sheets up. But what we've tried to do is transform that technology as well. So what we're doing here is that we're telling the software that we have a template. We have a DWT file, an AutoCAD template. And what we're going to do is send both that template and the road up to the cloud, and the software is going to generate the plans for us. It's going to set up those plans and the profiles. So we're just giving the software some more information about how much information we want to include on these plans. And we're going to tell it what sort of scale we're going to use, so 1 to 500, 1 to 200, whether we want to see the plan and the profile, so whether we want to see the road in top-down or in the profile view. And it's going to open up the native application when it's done. It's very, very quick. And what you're looking at is a road alignment with the sheets. So it's created 12 sheets and the alignment. It's set all up the overlap. It's set up everything. Done. And there's our paper space. From there, we need to do more detailed work, but essentially that's taken a lot of the pain away from setting these things up. So the next thing we look at is mobility, and we've heard a lot of talk of mobility, and again, we need to do more work in the infrastructure space. But what you're looking at is me navigating on my iPad, and this is, think of this as an infrastructure design or a design of an intersection or a new car park. And what I'm about to do is I'm about to make a comment on this, and every one of my colleagues that's associated with this model will see this comment. Now, I made a typo here, so excuse. But what I'm basically saying, let's take a look at that intersection. There's something wrong, I think, with that intersection. And I might be on site, I could be in a design meeting, I could be anywhere. I put a little push pin so that all the users know where that issue is. And looking at the design feed, there it is. Now, if I go back in the native application inside the desktop version, I'll see exactly those comments as well. So there's a real social element now to these models, and it really hinges on the collaborative process that we go through. One of the other technologies that we work heavily on is this idea of turn path solutions, and the idea that we can digitally simulate things in the model before we even go out on site. And what you're about to see here is a low loader. And that low loader, we're simulating coming through the intersection. It's doing the turn path, but there's a problem. And there's the problem. The low loader clips the curb, but notice how each axle acts independently. It's giving us that immediate feedback. So that fails. And so before we even construct that, we know it fails. We need to do some design changes. We not only can do it in a 3D space, we can also do it top-down view as well. So looking at the 3D view, we can simulate these vehicles coming through the intersections or the junctions and see exactly how they'll perform. That passed. That's good. You're looking at Oculus. So we support Oculus as well. That, again, is an emerging technology, so we can plug the Oculus into these models. You're just looking at a colleague of mine staring around. It looks quite funny, but actually when you're wearing the Oculus, it's absolutely incredible. And you can see the two views on the screen, so he's having a great time. He looks a bit mental, but that's good. We've heard a lot of talk about point cloud technology, and I'm really happy to say that I'm glad to hear that, because for the past 10 years I've been evangelising this technology, and I have to say finally the architects get it. Good. Excellent. Keep going. So point clouds are not new, but what's new is what we're doing with point clouds. So what you're about to see is an example that I did in Sydney recently, and what you may notice in this scene is that I'm doing a laser scan, which everyone's quite familiar with, but what you probably didn't notice is that there are no targets. There are no spheres, there are no paper targets, there's no survey control, there's no total stations, and that's because the technology that we've built enables us to choose common points between those point cloud scenes and register those point clouds together without any targets. It's a very efficient and quick way to do it. I did 7 scans here in Martin Place in Sydney, and this is the type of data that we can get. It took me a morning to do. I went very early in the morning so that the traffic didn't get in my way and people didn't ask me too many questions. And this is the type of data that I got within 1 day. The other thing that we can do is that we can go into this immersive environment. So we go into what we call these 360-degree views, and they're just the camera views. And I think Chris pointed out that before, that these are quite important when we want to have a look at things at a higher level of detail. The other thing that we look at is this technology that we can take photos and make point clouds. So this is an incredible technology. So what we're doing here is that we're flying a little drone over San Francisco, and a GoPro is attached to that drone. Now, every 5 seconds, the GoPro is taking an image. And what we're about to do is we're about to use the cloud to upload those images. And from those images, the cloud service will create a point cloud. No scanners, no total stations, just photos. And that's what we get back. So this is transforming reality capture. This is transforming technology in the reality space. It's an incredible technology. So what's the future of reality technology? Well, what you're looking at, and it might be hard to see, is what we call the recap robot. And it's a laser scanner positioned on a robot. And the laser scanner goes around automatically, scans, registers automatically, and moves on. And it knows where it's been, and it knows where it's going. And it's completely automatic. And so on board, there is a computer, and you're looking at the registration process now, so it's doing the automatic registration. It's just wheeling around. It's not going to hit the wall. It's not going to run into someone or a person. And it's doing the registration on the fly. Now, think about this technology where you need to capture data where a person shouldn't be. Maybe a plant that might have had some issues, or anywhere where you don't want someone. This could be completely automated. And in theory, it could run 24 hours a day, 7 days a week. So we're thinking very deeply about these challenges and issues, and we're doing things to solve them. So the next thing that we're going to do is transform construction. So what you're looking at are surveyors, and they're looking at plans, and this is in the 1950s. Now, you might be shocked to know that even though the technology has progressed, the process really hasn't. Surveyors still use a whole heap of plans, a HP calculator, they do all the calculations on site, they dumb down the BIM model. And they go out on site and they do a manual set-out method. Not so much manual like that with a chain and a plumb bob, but they do a manual process to do the set-out. And what that does is that introduces risk. If you are taking a BIM model and you are then doing calculations from that BIM model, then you are introducing potential errors. So what we've done is that we've decided that we're going to take the BIM model out on site. We're going to attach it into an iPad. We're going to have it talk to the total station. No calculations. The BIM model will be in the field with us. So here's someone doing some set-out. They're using the new TopCon system. We talk directly to the Revit model. So once we've done the as-built process, those as-built points get fed directly back into the Revit model, the BIM model. And there are quite literally no calculations that need to be performed. We have all the grids, we have all the elements, we have all the structures, we have everything, and it's all hosted on the iPad. It's a very efficient way of doing survey on site, on construction sites. And you're seeing someone now doing some as-builts of these penetrations in the slab. And if you get these penetrations wrong and they pour the concrete, you're in big trouble. So they need to be right. They need to be correct. we're looking deeply at analytics. So with BIM for infrastructure, it's not purely about designing roads and bridges and drainage and rail. It's really about transportation, and it's about how we get from A to B. And we're thinking deeply again about this process. And what you're seeing here is an intersection at Elephant and Castle in the UK. And what you're actually seeing is an as-conditioned model. So this is as the traffic is at the moment. Now, what we can do with this technology is that we can start making changes to this model, and then we can see how the traffic flow and the pedestrian flow is affected. Now, that affects deeply what we do in a design space, and not just in an infrastructure space, but obviously a building space. This is Shibuya intersection in Tokyo. This is one of the busiest pedestrian intersections in the world. And we've modelled this as well. So what we're looking at is what we call a node-to-node analytic of an actual person. So how long does it take that person to get from A to B? And what if we make changes to the model? How then does it affect the person getting from A to B? And where you have big data sets like this, it's a very important analytical model that you need to perform. So I just wanted to show quickly some examples that we've done very recently in this space using this technology. And the first example is a roads and highway project that we did in the Northern Territory with a consultant in Australia called SMEC. And SMEC actually won the project using this technology. So they sat in front of the stakeholders and they made changes to this model on the fly, and they actually won the project. Now, this project took 5 days to build and not 5 weeks. So it's transforming the way that we do these designs, it's transforming the bid process, and it's transforming winning these projects. And the knock-on effect is that the model looks stunning. It's beautiful. We're about to see, I think, the emergence of a new technology, and it's not BIM, it's UIM, which is Urban Information Modelling. And this is going to be a very powerful analytical tool along with the commuting tool. This is a project that we partnered very recently with GHD in Sydney. They're a very large engineering consultancy firm, and they tendered on a very large project in Sydney, an urban development project. One of the things that they wanted to understand was how some of the suburb analytics would affect the design. And there's only one way to do that, and that is to build the city and build the analytics. So what you're looking at are some project areas. So we're looking at the areas of influence for this project, and we're able to leverage tools like GIS to do this. So we bring in the GIS data, we can colour the GIS data, it gives us this immediate feedback of what's going on. Once we do this, we can then look at things like the analytics. So you're looking at a 3D thematic map of some of the suburbs statistics. And what we're looking at is some 3-bedroom dwellings by suburb. And that affects where we put a rail line. We know that the people on the eastern quarter don't so much catch the train to work. And it's a pretty simple tool to view the analytics. So method of travel by train, obviously the people in Newtown travel by train because there's a train station there. It's pretty straightforward. But it's a very powerful tool to view. So now we want to look at things like optioneering. So once we understand the makeup, the demographics, the statistics, the analysis, it would then be very powerful to start doing some mock-ups and doing some design iterations. And so you can do that inside InfraWorks as well. So what we're doing here is that we're starting to just sketch a road, and it might be a path, just linking one side to the other. And it's very easy to do. It's completely interactive. You're doing it in Canvas. It's giving you immediate feedback. So wouldn't it be great now if we put our BIM models in here? Well, we can do that as well. So we can drop our models inside this larger model in Canvas, and then we can see how they perform. We can look at things like the sun, the solar, how they interact with other buildings, how they interact with the community. And we can do all this again in a matter of minutes and not hours and days and weeks. And it's very easy to place these buildings in. If the buildings are on a geographic system, it will understand those and it will place them in accordingly. But for this example, I've just mocked them up. I've just placed them in, and I want to see how they perform. So now we can look at things like the sun, and we can look at moving the buildings. You can see that the shadowing is live. That shadowing is real. We know where the sun is, we know where the shadow is, we know where the building is. So we can move the buildings accordingly, and we know how they'll perform. So let's move that sun. What happens if we want to have a look at the summer and winter solstice and the vernal equinoxes? So let's move the sun. Let's do that. So we can do that as well. So we simply select some of the tools and simply change the time of year, the date, and the time of day. Very simple. Very powerful. The last example I want to show is a very large example of a project in the United States. And I guess this is a hyper example of BIM for infrastructure, but I've termed this BAM. And it is an acronym, and the first is building, and the last word is models. And you can figure out yourselves what the second acronym is, but they are very big models. So what we're doing here is that we're zooming around the Port of Long Beach. And this is a model that was completed from Parsons Brinckerhoff in the United States, and this is for the California High-Speed Rail project. And what PBs did is they actually went and built California. So what you're about to see is a fly-through through the city of Los Angeles. Now this fly-through was done all inside the technology. It wasn't done in any other technology, it was all done in Canvas. You're about to fly over, I would suggest several 100,000 to almost 1 million buildings that were built automatically from GIS data. So we simply tell the software to build those buildings from the footprint, and it will go away and do it. None of this was done manually. Once we get to specific areas, we can then look at some design options as we did before. And one of the options that we want to look at is the change to this bridge. So again, in Canvas, we can have a look at design option A and design option B. And just in Canvas, change those options. This is transforming cities. Let's do a fly through now. Let's fly underground. Let's have a look at some of the architectural data that we've leveraged. And you can see it's a twin tube tunnel and some station boxes. And again, we're looking at all this in Canvas, all in the one product. No jumping in, no jumping out. It gives us an immediate feedback. And then we can have a look around the city, and then we can fly out of the city and have a look at the design alignments. So again, this is transformative technology, and this is what we're working on at Autodesk in this space. And this is all of this technology that you've seen today is available now. And with that, Rowan, thank you.